So chapter 5, we're going to shift gears a little bit. We now have learned all about derivatives. That comprises, I want to say, like 50% of what calculus is about. And now we're going to start with what we call integrals, and that's another 50% of what calculus is all about. We're going to do things in a different order. So I'm going to do 5.1, then 5.5, then 5.2, and so on. And, there's really not a specific reason. A lot of these things, don't have to be done in the order that the publisher chooses them to be. Okay? All right. So let's get started with 5.1. We're going to talk about distance traveled first. So look at this situation. A train moves along a track at a steady rate of 75 miles per hour. Okay, so a few important things here. First of all, there is a steady rate of 75 miles an hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Now, I know you can do this in your head. I get it. But we have to, I've chosen a very simple exercise for a reason, right? It's because we don't want the intricacies of a problem. We just want to talk about a simple case. So let's talk about what we have here. We're given a steady rate of 75 miles an hour, okay? So we can say that, our rate is 75. And if this train is traveling from 7 a.m. to 9 a.m., then that's a length of 2 hours. So my t is equal to 2. Okay? So we go to our very basic formula about distance and rate and time. Distance equals rate times time. And if we want to know the distance that's traveled, we can say, well, the distance is 75 miles an hour times 2 hours. And when we do this, the hours will cancel. And so I have that the distance is 150 miles. Okay, we could have done that in our head, but I want to do a little bit of dimensional analysis here, units, dimensional analysis. We had a rate. We needed to find distance. So in order for us to do that, we had to multiply a rate by a unit of time. Okay? That's the only way to get distance. You have to multiply a rate by a unit of time. Okay? So keep that in mind for a minute. All right, so let's make some connections here using a graph. Here we have a velocity versus time graph. What we were given when we say rate, that's another word for the velocity of this, right? And it's a steady rate, meaning constant, right? So we are given that v of t, if we write it in function form, is 75. And if I graph that, that's what that looks. So now he's traveling. And now let's go on our time axis. And let's calibrate our time axis here. And, suppose this starts at, whichever time. And then when we go further in here, this is 7 a.m. and this is 9 a.m. So what we're looking at is that this train traveled at a steady rate from 7 a.m. to 9 a.m. Okay? That's a total of 2 hours. Okay, now I have my rate and I have my time. What do I have to do with these in order to get a unit of distance? Multiply them. So now, if this is the length of time, okay, and if this is the rate, which I have to multiply, geometrically speaking, if I multiply, raise your hand for this please. If I multiply the red times the blue, what quantity have I found? The area here, right? So when I multiply rate times time, I have found the area underneath this curve. Okay, so the area represents rate times time. Okay, area. I'm sorry, distance. Yeah. Okay. So if we just go with the area, area is base times height, which is 2 times 75. Lo and behold, it's 150 miles if we include the units, right? So I know that if I gave you that problem up above here, you could have solved that. You're in AP Calculus. You could have solved that bullet point. Like, if I gave it to you while you were walking from here to your locker, you'd be like, it's 150 miles, right? But the point of this simple exercise is to figure out this, right? That underneath is the area. So now, yes. So what conclusions are we going to make here? That the distance traveled by the train is exactly the area of the rectangle whose base is the time interval and whose height, this is the thing, the height at each point is the value of the constant velocity function. We've come across this before, okay? In the last chapter, when we were looking for like the rectangle under a curve, we had x and then the vertical was the y value, correct? That was y. So I spent an incredible amount of time outlining that because here we're going to use it, then we're going to use it again in chapter 7 and so on. Okay, so let's go into another fundamental problem then. Okay, I had a velocity function, all right, and I had a time interval. I had to find distance based on my velocity and my time interval. So given rate and time, I needed to find distance. And we just came up with the fact that, oh, that's just the area underneath V of t. Okay? So this is area under V of t. Now, because this one, the velocity was a steady rate and it was constant. When I drew my velocity function, I got a straight line up here. And so when I had to do the time interval times that height, I got a perfect rectangle, 490 degrees. The only way, the reason why I got a perfect rectangle is because that velocity is a constant function. Now, how many of the functions that you run across in math are constant functions? Very few, if any. All right? So what if, I lucked out for this one. I got a rectangle underneath and it really worked out in finding my area. So now what if the train had a velocity that varied as a function of time? What if it wasn't constant? What if it had to stop and slow down and speed up, right? Like, what's going to happen then? So, So what if our velocity looks something like this? Okay, now this is V of t. The question now is, would the area, okay, and so we're going like from 7 a.m. to 9 a.m. Okay, look at the area underneath this now. Is that a rectangle? No. That is not a rectangle. That is what we call an irregular shape because it's not one of the polygons that we have formulas for. So the question now is, would the area of this irregular region still give the total distance traveled over the time interval? Yes. If I found the area of this, is that still the same as the distance? And the answer is yes, right? when you have to find the area, you still have to multiply a time interval times v of t. That's still distance. Okay, so the area is still distance. The question now is, the area underneath is not a perfect rectangle. How on earth am I going to find the rectangle now? Boy, life was easy when I had to just find the area of a rectangle. So, Isaac Newton and Leibniz, who both, I've gone over this independently, you know, they like wrote all of calculus. What they did is this. They said, okay, if I could do it when it was one big rectangle, what I can do here, right, is I can partition this into tiny, tiny triangles. So if I get that same curve up there, here, they said if I could do it when it was one big rectangle, well, you know what I could do? I could draw it so that there were tiny, tiny little rectangles here. Right? Look, if I drew tiny, tiny rectangles, right? And I found the area of each and every single rectangle, right? That would eventually give me the area of the entire region. Do you guys agree? Okay. Huh? Yeah. So what you have to do is you have to find the area of every single one of these rectangles and then add up all the areas. That's a lot of rectangles to add up. Okay? So now I know that, you know, like if I zoom in here and if I make that a rectangle, right? Do you see how like there's a tiny little empty space that's not covered, right? So I accept the fact that there is a slight approximating that we're doing here. But one thing to get around that is just make more and more rectangles. Like if I divided this into more rectangles, then that space would be covered up more and more and more. So that's the trick behind it, okay? Okay, yes?
Does it matter that it's like not constant velocity?
Well, that's why we're doing tiny rectangles. If it was constant velocity, we'd get away with one triangle. Yes?
Or one big rectangle. My question is, so are you saying that as you get infinitesimally smaller and smaller rectangles, the approximation gets closer to the actual value?
Yes. Yes. Okay. So they argue that the total distance could be found by summing up the areas of the rectangular strips. So what we're going to do is area equals base times height for every single rectangle. And so how do I find the base? That's the length of each rectangle on the x-axis or the t-axis. And then what's the height? The height is the function, right? That's determined by the function. So its velocity in this problem. Oh my God, let me finish. Process is called rectangular approximation method, okay? Because we approximate the area by drawing rectangles. Okay, so what we're going to do, the process is draw a series of rectangles, find the area, add them all up. Okay, find the area of each, add them all up. So if we have rectangles, their width is determined by the length of each subinterval. Get used to that word, subinterval. If you look here, 7 a.m. to 9 a.m. is the interval that I'm working with, and then I divide them into subintervals. So the length of each, the width of each triangle is a subinterval, okay? Now, the height of each rectangle is determined by the function's value at each end point. Okay, now, there are several ways that we can draw our rectangles, right? So if I had a curve like this, and let's say I made 1, 2, 3 rectangles, okay? Or I'm partitions. All right, so I'm going from here to here, from A to B. So I have 1, 2, 3 partitions here, right? Subintervals. Okay, so for each one, I can make it like I have to now close the top, right? I can use the left endpoint for each rectangle to make it a rectangle, right? The left endpoint of each subinterval, and it would look like that, right? This is called left-hand endpoint, and for short, we call it LRAM, left rectangular approximation method. RAM stands for rectangular approximation method. This is when we use the left endpoints of each interval to determine the height of the rectangle. Similarly, what I could do is I could have the right endpoints, right? I could use the right endpoint of each triangle and make it of each interval and make it a rectangle like that. That's RAM when I use the right endpoints. Or I could top it off at the midpoints of each of them. Okay, that's midpoint MRAM. Okay, so let's do an example and then you'll see what we're talking about. I have actually drawn it here. So look at what we have. Estimate the area under the curve of f of x equals x squared from 0 to 3 with 6 subintervals. There are 3 pieces of information you need to know here. X squared. You need to know x squared. You need to know that it's from 0 to 3, and you need to know that there are 6 subintervals. So the base of each rectangle, that's the width of each subinterval, right? Okay, I have a full range, 0 to 3, which I'm dividing into 6. What I do is this minus this, right? So 2 minus 1. So I do 3 minus 0 divided by 6. That's 1/2. That's the length of each rectangle, the width of each rectangle. So if I'm going from 0 to 3, here, if I do LRAM, you see how I make my left endpoint the top of the rectangle, okay? So the first partition will end at 1/2 because that's the length, and then 1, and then 3 over 2, and then 2, 5 over 2, and then 3. Okay, so here is what LRAM will look like. You literally have to now sum up all the areas of the rectangles, okay? So what you have to do is you have to do base times height. The base for the first one is this right here, that rectangle, right there, right? It's at 0. So the base is 1/2 times the height, that's the function evaluated at the left endpoint of 0. So that's 0 squared. Plus, what's the base of the second rectangle? 1/2 times the left endpoint squared. The left endpoint squared. Plus 1/2 times, now I'm on the third triangle, 1, 2, 3. The left endpoint is 1 squared. Why squared? Because it's f of x equals x squared. Plus 1/2, 3 over 2 squared. Plus 1/2, right? Yeah, there is a lot. Plus 1/2, 2 squared. Later we'll do that. Plus 1/2, 5 over 2 squared. So what's the last one that we do? This triangle, right? So you need to have as many terms here as you have subintervals. So 6, right? 1, 2, 3, 4, 5, 6. You add it all up and it's 6.875. Okay, now, do you notice how for each one, because they're equal subintervals, it's always 1/2 times. So yes, you can pull that out of the equation. So we're going to do that now. Like you see how you have all these halves here for the base? I can pull that out. I can factor it out, and I could do it that way. Yeah.
Why don't you include 3 if you're doing it the left hand?
Because for this rectangle, the left hand is this one.
Oh, and there's no left.
Yeah.
Oh, so the left hand is like.
The left end point.
Got it.
Okay. Now we're going to do RRAM. So it's going to be the base times each individual height, right? So we're going to do 1/2, that's the base, times. Okay, now we're going to do the right endpoints. So the right endpoint here is 1/2. I like to write them here. So it's 1/2 squared plus, for the next rectangle, the left endpoint is at 1 squared plus, for the next one, it's at 3/2 squared plus, it's at 1 squared plus, it's at 5/2 squared. Oh, that's a 2, sorry. 5/2 squared. Are we done? No. And then the very last one is 3 squared. And so now we get 11.375. Do you see how much difference there is from the first to the last? When I did LRAM, right, I under approximated because there is all this empty space that I haven't taken into my rectangles. When I do RRAM, I'm over approximating because now there is all this extra space that's not part of the area. So MRAM has to be the middle somewhere, right? So let's do MRAM. For MRAM, I now want the midpoint of each interval. So if each interval goes from 0 to 1/2, now it's the quarters. So this is 1/4, 3/4, 5/4, 7/4, 9/4, 11/4. So for each rectangle, it's going to be the base of 1/2 times that f of the midpoint. So 1/2 times 1/4 squared plus 3/4 squared, 5/4 squared, 7/4 squared, 9/4 squared, and then this one. We put it in our calculator and we get 8.9375. And as expected, that's between the two. Okay? How do we get it to be less of an approximation and more exact? By doing what? Not MRAM, but what eventually? More and more and more rectangles. Instead of 6 rectangles, 1,000,000, 1,000,000,000,000, a bazillion. Okay? My kids are always asking me, like, what's after 1,000,000,000? And I'm like, 10 to the 15. It is, though. It's 10 to the 15. Okay. So the table shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1 with LRAM and RRAM. Okay? So it has a length 1. If I were to graph this, right, t-axis would be on the bottom, so those would be my base widths, right? And you see here the intervals from 0 to 1 is 1, 1 to 2 is 2, right? So here I have a base of 1, and so on and so forth. This is the velocity, that is the height, right? Because I have t and v of t on my axis. Now, if I go here, my first point is at 4, and then at 12. I didn't make this large enough. So if I were to draw my points, they would look like this. Okay? So if I were to do LRAM, left endpoint, what would be the first endpoint I take? F of 0, which is 4, right? So here's what we do. For LRAM, we're going to do the base, which is 1, times, you're already given the y values now. There is no calculating to be done. You just have to know which one to start with and where to end. So if I'm going to start with the 4, right, because that's the left-hand side, then it's just all the numbers starting at 4 until the second to the last one. So 4 plus 12 plus 22 plus 10, 5, 13, 11, 6, 2, 6. Okay. No, we're not squaring them, because the reason why we're squaring them before is because we were given the function. Now you're given the actual value. Somebody did the squaring for you. This gives you 91. And what's the unit if this is for the distance? This is a model train. It's going in inches, not miles. Okay. The RRAM, I would love that model train to be going 91 miles. That would be Guinness Book of World Records. RRAM is going to be the base times, now I'm going to take the left endpoint, so I start at the 12. Okay? So it's going to be 12, 22, and then I go until the last one. 6 and 2. And that'll be 87 inches. So, next. A particle starts at x equals 0 and moves along the x-axis with a velocity of 6 for t is greater than 0. Where is the particle at t equals 6? Right? So, take a look at this. It's a constant velocity of 6. It starts at 0 and it goes until 6. You want the distance that it traveled, right? The distance that it traveled in the 6 seconds is 6 times 6, 36. Now, what if it's not so simple? What if a particle starts at 0 and moves along the x-axis with a velocity of negative 2t plus 6? Now it's a different function, right? It's a linear curve, okay? Y-intercept is 6. Where does it cross the x-axis? At 3. Okay, so v of t is equal to negative 2t plus 6. Now, if I want the distance, I need the area under this curve, right? Any graph, the graph of any function is a curve. So v of t is equal, I'm sorry, not v of t, distance is equal to half, this is a triangle, times the base times the height. So that's 9. Is everybody okay with that? Yes? Okay. A car comes to a stop 10 seconds after the driver applies the brakes, right? So you apply the brakes and then it takes 10 seconds for it to slow down. While the brakes are on, the velocities of the car are listed below. Use the midpoint approximation with 5 subintervals of equal length to estimate the distance the car traveled while the driver was braking. Okay? So, if it takes 10 seconds and we want 5 subintervals, how much is each subinterval? The base is the subinterval, and it's 2 seconds, right? 10 into 5, it's 2 seconds. So, if my first interval goes from 0 to 2, and then the next one goes from 3 to 5, but I want the midpoints, then I have to take the middle values, literally the middle values. No. Oh, no. Sorry. Huh?
Wouldn't you add like 88 and 76 and divide it by 2 to find the midpoint?
So if you think about it from 0 to 10 partitioned into 5 units, each one goes to 2, then the midpoints are, the 1, the 3, the 5, and so on. So the 1, the 3, the 5, the 7, and the 9. Okay? So those are my midpoint values. So MRAM, it's going to be base times height. If my base always has a width of 2, the heights are these values. Okay? So the first height we take is 76, then 57, 42, 29, 3, and so that's 2 times 207, 414 feet. Okay? 10 seconds is a long time. It must have been like a very gentle break. Yeah. It makes for a good problem though. But he was going at 88, let's just be fair, at 88 feet per second, and then, so he had like 88 feet per second to come on. Right, it's not that many, but you still have to go from like 88 to 0 no matter what units. Okay. It's a lot. It's pretty fast. Yeah, it's very fast. Okay, so let's go to here. This table records the velocity of a car in miles per hour at different time intervals over 25 seconds. Okay. So here, this is what is important here. You missed the 3 most important words in my sentence here. It records the velocity in a car in miles per hour at different time intervals over 25 seconds. So if you look here, the first time interval, t equals 4. The second one, t equals 2. So you've got one rectangle which has a width of 4. The next one has a width of 2. The next one has a width of 3, right? And then, so you have to go and you have to do these. So in all of the language that I spoke to you guys about today, I purposely never used the word equal. I said you make rectangles. I never said you make equal rectangles because there is no restriction that your rectangles have to be equal to each other. Okay? If you like to be, a rebel and live on the dangerous side, that's fine. Okay? So what you have to do though, now, the only thing you can't do is you can't pull out the base because it's not constant. So for each one you have to do base times height, base times height, base times height. So you have to calculate all of the different bases. So here, yeah.
But time is in seconds and velocity is in miles per hour.
Yes, and we're going to take care of that right now. That's another thing. So t is equal to what here? 4? No, 1. And then 4, and then 3, and then another 3, from 9 to 10, and then another 1, and then a 4. Okay, so you have to do every single one. So those are my bases, and these are my heights. Okay, so let's go ahead and do this. So LRAM I want to keep the units for now. LRAM is going to be 4 times 0. Okay? Right? LRAM means you have to take that left endpoint, right? So it's the 0. Okay? And then plus 2 times 20, 3 times 31, 1 times 47, 4 times 50, 3 times 52, and then what else? 3 times 54, 1 times 60, and then 4 times 56, and you already know that you're done because you ran out of bases, right? Yeah, right? You ran out of bases, and you know that with LRAM and MRAM, there's going to be one on either end, one on an end to be left out. So now I have 982, but what are my units? My units are miles per hour, and then I multiplied that by seconds, right? That is not the right unit. I need to convert this hour into seconds. How am I going to do that? Multiply or divide? We divide. Okay? So we're going to do times 1 hour is 3,600 seconds. So if you think about it, if it's 982 miles in an hour, it has to be a lot less in a second. So I have to divide, right? So it's 982 over 3,600 miles. That's it. 1 sec. And this is 0.2727 miles. Okay. Now, so that's how many miles. That's it. Do you know how to convert to feet? If you needed to. What's the conversion? 5,280 if you needed to convert to feet. Okay? Yeah. Okay. I have to get the new software, but I wanted to send this to you, and eventually I will when I get this figured out. But this is a little exercise for the TIs and for Riemann sums. So basically, it shows you how what the approximations look like, whether it's a left midpoint or right approximation. So now it's set on the left approximation. So here, we're going to look at the area from A to B. So if I go with, let's say, 3 rectangles, that's how it looks, right? Left approximation. If I wanted to do a midpoint approximation, that's how it looks. Right approximation, that's how it looks. So now, if I increased, so you see how this is not a very good approximation of that area at all? But now if I went to more triangles, look, it's more rectangles. Now it's getting better. And if I went to 10, 11, it's getting better. And if I went to 14, that's even better. I could do better than that, though. 18, right? So look, as you increase the rectangles, do you see how it's such a better approximation? Right? Look at this. As you increase, it just fills in. So this is now in the minds of Newton and Leibniz now, right? This is what they were thinking. They're like, well, you just keep adding, and look at that. Yeah, I'm sure they were on their TIs doing simulations in those days, right? So this is all, with, and then this, right? Not cool at all. So if I wanted to do the right endpoint, oh, I wanted to do the right.
Wait, what's the T?
Tomorrow. If I wanted to do the right, and look at the right endpoint, right? We're over approximating, but look, they're getting better. extra spaces are becoming less and less and less and less and less and less until finally it's a perfect approximation. And then you can do this all day. If I do the midpoint,
Isn't midpoint like more like most accurate? Why do they do like the left and the right?
so okay, wait. Let me answer that. I get paid for this. So it actually depends on the type of function, and you will see that. I know. It depends on the type of function, and you will see that for different functions, left endpoint is an over approximation. For other function, left endpoints is an under approximation. And so it depends on the function, really. And so if you do like the midpoint, look at that. Look at how even. Look at that. Isn't that amazing? That's fantastic, huh? Again, it depends on the function.
Like the triangle, then you can like flip it and then it goes in. I mean, I don't know that.
Right, one is the inverse of the other. Correct. Okay, so a little bit of